Here we're going to look at the pigeonhole principle. So, let's say you have a drawer full of black and white socks. Without looking in the drawer, how many socks must you pull out to be sure that you have a pair of the same colour? Well, I guess you could be unlucky and pick 2 socks out that are different, but the next sock you select is going to have to match one of those other socks, so it will be 3. Trying to spice up your life, you go and buy a large number of red socks, green socks and blue socks, and you add those to the drawer. Now how many must you pick out to be sure of having a pair the same colour? Well, you could be mega unlucky again, and the 5 socks you pull out, black, white, red, green and blue, aren't going to match. But the very next sock, the 6th sock, is going to have to match one of those ones you have. Now, being of a mathematical persuasion, you have n different coloured socks in your drawer. Now, how many must you pick to be sure of having a pair of the same colour? Did you have n plus 1? If you were again crazily unlucky and you had to pick every one of those colours out before matching a pair, but you've exhausted all of those colours, then the very next one that you select will have to match one of the socks you've got laid out in front of you. They're socks worth showing off. So this principle, the pigeonhole principle, is another counting technique, and it's used to solve problems. I'm going to say they're usually not all that easy. If you have more pigeons than pigeonholes, when the pigeons fly into the holes at night, at least one hole has more than one pigeon. So Johann Peter Gustav, not sure, German mathematician. He's the fellow who made many contributions to number theory and to the theory of Fourier series and other topics of mathematical analysis. He's credited with being one of the first mathematicians to give the modern formal definition of a function, actually. So more formally anyway, if you place n plus 1 objects in n holes, then at least one hole must contain more than one object. So 9 holes and 10, which is 9 plus 1 pigeons, for example, that pigeon's got to land in and be with somebody else. So at least one hole contains at least 2 pigeons. So for the pigeonhole principle, if n is a positive integer and n plus 1 objects are placed into n boxes, then at least one box contains 2 or more objects. For this proof, we use a proof by contraposition. Now, a proof by contraposition is an indirect style of proof that skirts around the problem and finds a clever argument that produces a logical contradiction. Suppose none of the n boxes has more than one object. Then the total number of objects would at most be n. This contradicts the statement that we have n plus 1 objects. Here's some examples to try and get our head around it. In a group of 367 people, there must be at least 2 people with the same birthday. Why do I know this to be true? Well, there are 366 possible birthdays in terms of, there's 365 days, but the 366 days in a leap year. So if you have another person, there has to be a double up somewhere. In a group of 27 English words, at least 2 words must start with the same letter. Why do we know this to be true? How many letters are there in the alphabet? There's only 26. So if you have another word, there has to be a double. In a packed Carnegie Hall performance, there will be 2 people who have the same first and last initials. That's because each initial can take one of the 26 English letters, meaning that if you consider their first name and their last name, that's 26 by 26, which is 676 possible values for the first and last initials. But the main hall at Carnegie seats roughly 2,800, so consequently, 2 of the patrons, at least, on a sold-out show must share the same first and last initials. In the movie Cheaper by the Dozen, there are 12 children in the family. Prove that at least 2 of the children were born on the same day of the week. Well, there's 12 children or pigeons, which we are placing into the 7 days of the week, which are the pigeonholes. So by the pigeonhole principle, some day of the week must have 2 children. There are 800,000 pine trees in a forest. Each pine tree has no more than 600,000 needles. Show that at least 2 trees have the same number of needles. Well, in this problem, the 800,000 pine trees are the pigeons, and the 600,000 different possible numbers of needles are the pigeonholes. So one tree could have 1 leaf or needle. One tree could have 2. One tree could have 3. Another tree could have 4, all the way up to 600,000. You've counted 600,000 trees there. There's still a whole stack to be placed then, in terms of there are 800,000 pine trees to be allocated. Okay, let's generalize it with some pronumerals and rules. If there are n objects and they are placed into k boxes and n is greater than k, so there are more trees than pine needles, then there is at least one box containing n over k objects. Now I want you to note these different brackets. They're actually called ceiling brackets, and that's the ceiling part you can see up here. So what that means is we actually have to round up. I'll give some examples as to how that works. So if there are 100 people, what is the minimum number of people that will be born in the same month? Okay. In this example then, the 100 is your n, that's the number of people. The number of places you've got to put these, the pigeonholes, is 12 because there's 12 months in a year. When you simplify 100 over 12, you get 8 1/3. The ceiling brackets tell us to round up to 9 people, but of course we need whole people anyway. You can't have 8 1/3 person. Second example. There are 5 colours of crayons to select: black, red, white, pink and blue. How many students in a class must there be to ensure that 6 students select the same coloured crayon? Try it. Let the boxes be the colours, i.e. k equal 5. We want the number of students, that's what we're after, that's n. And we know that the n over 5 needs to be equal to 6. What are the possible answers here? You could have 26, because if you have 5 1/5 using those ceiling brackets, you would have to round up to 6. So the lowest possible value for n is 26. A bowl contains 10 red and 10 yellow balls. How many balls must be selected to ensure 3 balls are the same colour? In method 1 is to consider the worst case scenario. So that would be first collecting 2 balls of each colour, i.e. first 4 balls. So it's the next colour that will give you 3 the same. So that means the answer is 5. If you use the generalized pigeonhole principle, how many balls are required? If there are 2 colours, one colour must have 3. So how many pigeons are required? If there are 2 pigeonholes and one of those must have 3 pigeons in it. The number of boxes, k equals 2, and we want n over k to be 3, which is where we were at a little while ago. N over 2 equals 3, so the smallest possible value that will leave you with an answer of 3 is 5. Same in that you have a bowl containing 10 red and 10 yellow balls. How many balls must be selected to ensure you get 3 yellow balls? Well, consider the worst. I think it's the easiest way to do this question. First, selecting the 10 red balls and 2 yellow balls means you've got 12 balls. It must be then the next choice will result in 3 yellow balls, so the answer will be 13. 6 computers on a network are connected to at least one other computer. Show that there are at least 2 computers that have the same number of connections. The number of boxes k is the number of computer connections. This can be 1, 2, 3, 4 or 5. The number of pigeons n is the number of computers, 6. So by the generalized pigeonhole principle, at least one box must have the ceiling brackets n over k objects. So that's 6 over 5, which when you answer that and round up is 2. So at least 2 computers must have the same number of connections. There are 50 baskets of apples. Each basket contains no more than 24 apples. Show that there are at least 3 baskets containing the same number of apples. So this is how we can do it. The baskets are the pigeons, and we will place each of them in one of the 24 pigeonholes according to how many apples are in it. Thus, the ratio of n over k of pigeons to pigeonholes is 50 over 24, which is 2 1/12, and using those ceiling brackets, we round up. So there must be at least 3.